All right, so the warm-up says set up an integral to find the arc length along this curve between 2 points. So we have some sort of curve. We want to find the distance a particle would travel along this path between these 2 points. So the first question, I guess you could say, is are these points really on the curve? It'd kind of mean if I gave you points that weren't actually on the curve. And if we plug in x equals 0, we get a y value of 0. If we plug in x equals 2, we get a y value of 6. So these really are 2 points on my curve. So from here, I'm really just going by my definition for arc length. Arc length, I'll call it L, is the integral from x equals something to x equals something of the square root of 1 plus the derivative squared and then dx. Right, so it's my stock formula. And once again, I believe that's a kind of an important derivation just to see the process of generating it. So that was on the quiz and in the text, on the video and in the text as well. So if we just apply this formula, we're just integrating from x equals 0 to x equals 2. The square root of 1 plus, well, if y is x squared plus x, and the derivative should be 2x plus 1 quantity squared dx. And that's really it. That's the integral. And if we want to clean it up a little bit, we can. But we certainly don't have to. I could say, what is 2x plus 1 squared? It should be 4x squared plus 4x plus 1. And if I add 1, I guess I could write it like this. It's a little easier to input that way. Or plug into Mathematica or do whatever I wanted to do. That's it. That's what we would calculate for our arc length. Any questions about that problem? All right. All right, so a lot to do today. Administrative kind of notes here. So 1, our schedule has been changed. Schedule has been changed. So when I write out a schedule in general, I try to leave a couple fill spaces. You'll see them on the schedule as topics days. Those are my, if we start falling behind, those are my catch-up days. Otherwise, we'll use them for reviews and whatnot. So if we look at the new schedule, there's been a whole lot of changes. All we did was bump 7.2 back essentially, and everything else is bumped back. And then 7.7 and 7.8 we consolidate into one day. We should be able to get through most of those 2 sections in one day, but if not, it will just spill into the topics day. We should still be on track to finish all our content before the exam, so that will stay the same. Okay? So right now we're covering these 3 sections, not all of 6.7, just one little kind of subtopic I want to talk about. And then also 7.1 we'll get to. All right, then associated with that, the homework has also been adjusted a little bit. So the 6.6 homework should be due, it's like tomorrow night. So we're talking about that today. And then 7.1 is also due tomorrow night. And 7.2 has been pushed back to the 10th. So we'll talk about that tomorrow. Any questions about the schedule? Yep. Yep, exam will still be on the same date. One thing about the homework, so I'm listening to what you're saying, so it sounds like we're saying that that's a lot of homework. The problems take a long time to go through. They are challenging problems. So there's always a balance. Remember, this is a summer class. It's fast, it's condensed, so it's almost like we're covering 2 days in one day. So all the time builds from that. So like I said in the beginning of class, you should really be spending something like 4 to 5 hours outside of class for every class period here, which is a lot. That's really the expectation. At the same time, I want to be reasonable, so I'm trying to cut back these assignments a little bit. First 2 were 15 problems. Yikes, right? So we went down to 10. 6.6, I only put 5 problems in here. I was going to try to use 5 as my level from there on out. However, when we get into 7.1 and 7.2, these are integration techniques. It's just a lot of practice. The problems shouldn't be as long, so I'm going to stick with 10 in those assignments. As we get to more application stuff, I'll try to trim that back to 5, kind of pick through them. Okay? So I'm trying to scale back a little bit. Yep.
You originally had 15 for each section, right? So is there any way that you could give us a list of what those were in case we feel like we need extra practice in a certain section?
Well, I think if you just go to the study plan, there should be a big list of problems for all the sections. And I believe, let's look back at the platform here. but you should be able to sort them by objective. Right, so when I pick things out, I kind of look at the objectives I want, and I put questions that are based on that. Like for instance, 7.1, there's going to be kind of chunked out sections in the text that, this example of integral, this example. And so I try to pull about one from every section. So if you realize you struggle with one, you should be able to go to that study plan and grab a bunch of extra problems. And of course, you can always look at the text and work through those problems as well. And the nice thing about Chapter 7 integration techniques is we're really just asking you to do a bunch of integrals. So you can always check your solution with Mathematica, right, or your calculator, whatever. So it's kind of like you have the full solution key anytime you want. So you can do as many problems as you want. In fact, it's kind of a story I always tell. When I first came here to Tech to work on my master's, I was paired with somebody else who was from Jordan. And we were talking about, kind of preparation. He's excellent at calculus and everything kind of related to that. So how did you get so good at doing these kind of exotic integrals? I said, well, I went to Calc 2. And me and my friend sat down and we did all the problems in the book. I said, oh, so you worked on a lot of problems. He said, no, I did all the problems in the book. That kind of blew my mind, like every single problem in a calculus textbook. Wow, right? That's really the kind of level you need to get to. I'm not telling you to go do all the problems, but the more, the better. You really will see the benefits from doing a lot of problems. All right. Any questions? All right. All right, so we're going to get into section 6.6 on surface area. 6.6 on surface area. So we're going to take some sort of curve in this case and rotate that curve about some axis to generate some sort of surface. So it's really just like the volumes we were creating before, except now they're not volumes. Now if we were to take this curve and rotate it, it's kind of like you're getting that same shape. It's just hollow now. We're just talking about the surface on the outside, not the volume that it's enclosing. And we're trying to find that surface area. And so it's very reasonable to say, well, can't we just do it the same way? Can't I just cut a slice and then approximate and do all that stuff? That seems to be what we're doing for all these calculus-style problems. And so we might try it. I might cut a little slice right in here. And I might look at that as I have some cylinder. I might try to find the area around the edge of that cylinder. And it really wouldn't be too bad to do that. I would have some sort of circumference value here times some thickness. I might want to say that it's 2 pi r times my thickness, which in this case would be delta x. But it turns out there's going to be a little problem with this approach. We're going to be missing something. Now the reason we're going to be missing something is because we can do that for volumes. Right? As our slice gets smaller and smaller and smaller, we can think of this cylinder where I have a kind of just an actual cylinder with a straight edge here. As that width gets smaller and smaller and smaller, it's going to get closer and closer to the value of the real volume, which would be just a little bit of an angle here, right? Just a little bit of an angle. So it's not straight across because there's a little bit of a curve right there. But the difference in volume between this thing and this thing is going to be very, very, very small as that thickness gets small. But now what about for surface area? Surface area is a little bit different, see, because that little kind of difference here and here are very small compared to the volume we have here. When we talk about surface area, we're taking this little difference and carrying that difference all the way around our object. So that little difference is really a bigger difference here. If we think about just zooming in on these two kind of images, one we have straight across and the other one we might have some sort of curve. And as I shrink that down farther and farther, that thickness, well, it looks like this and this. But I will kind of maintain that difference. So the problem is I really can't slice this thing and look at a cylinder. But I can still follow our general process of slicing, because even though it might start off like this, and if I look at smaller and smaller slices, it won't converge to this, but it should get closer and closer to look like this. That line as I get smaller and smaller, should look closer to a line, not necessarily a horizontal line, but it will look closer and closer to a line. So the big idea is instead of looking at a cylindrical slice, I am going to look at a frustum. So that thing. And I can generate a formula for the surface area of a frustum. The surface area of that thing is going to be pi times the big radius plus the little radius times L, where this distance along the side is L. L is not the height here. L is the side length. And I can kind of start with that formula, just like we started with the volume of a cylinder, and we use that to find the volume of one slice and then generalize. We're going to start with this thing, the surface area of a frustum. And we can kind of show this geometrically if we wanted to. In fact, your book kind of goes through a process of generating that equation. But if we're going to use that equation as the surface area of one of our slices, well, that seems great. Now we should be able to just kind of add up all those slices. There's a couple things that are going on here. One, what is L? Like for our general frustum, it's this thing. But if I wanted to draw that in my picture, what piece would be L?
Radius.
So my radius, these pieces would be kind of like this distance and maybe this distance. What would be L?
Curve.
The curve here, this little distance right here, it's this edge. It's not just my thickness, it's not just a delta x. That's what we use when we're talking about the width of the cylinder. Remember, this is kind of counting this little length here, though. It's not just a straight length across, it's this length. But I know how to find this length. That's just a little distance along my curve. That's kind of like a little piece of the arc length. So I could think about the derivation of the arc length to get the piece that I need, but this is really just the square root of 1 plus my derivative squared delta x. In fact, maybe I should even write that as, until I take my limit, delta y delta x, like that, which will turn into the derivative here in a second. But that represents a little distance along my path. And so that's going to be our L piece. There's my little L. I have my pi over here. And then I have the sum of these two radius values. Now, one thing to think about before I actually move forward from here is that, does this make sense as a value here? The surface area of this thing. Well, one question I could ask to kind of see if this makes sense is what happens if this gets smaller and smaller and smaller? If this gets smaller and smaller and smaller and smaller, in fact, if I could kind of put them together, surface area should be getting smaller and smaller and smaller, but eventually it should kind of turn into the circumference value. Right? If you're going to be squishing this thing all the way down. But as I squish it down closer and closer and closer, these two distances, they become closer and closer and closer. So you can almost imagine that if I could squish it all the way down, the radiuses, I'd have two of the same circle. I'd have two of the same radius value. And if I think of what that means, if these were just the same, I would have 2 times the radius value. So I would have 2 pi r, and then I wouldn't have to worry about this, so it really would kind of turn into the circumference value. And so that process of squishing it down and finding that these two distances eventually kind of look the same thing we're going to do here. Because we could say, all right, my picture, the big radius is going to be the function evaluated at 1 point, and then the second radius value is going to be the function evaluated a little bit later, right, where that's x1 and maybe that's x2. And I can say that looks like the surface area of my slice. And to find the total surface area, then I want to add them all up. But I also want to look at the limit as my delta x goes to 0. This is me adding up the values. But now what is that limit going to do? That limit is going to take f of x1 and f of x2 and essentially make those values the same. Right? Because x1 is moving closer and closer to x2. So that's going to simplify just to say 2 times my function value. And then as I look at the limit, this delta y over delta x is going to turn into my derivative squared, and then I'll have dx. And so that's going to be my formula for the surface area when I take this curve and I rotate it about some axis. So we go through that process, we talk about frustrums and all this kind of stuff and kind of generate this formula. But then once we get it, and we're kind of looking at it, we can say, okay, this is kind of like a circumference piece. And this is kind of like, oops, should have an X here, I believe. And this is kind of like an arc length piece. So a very reasonable way to think about what we're doing here to generate this surface area is we're taking this distance and rotating that distance about some circumference value. So it kind of makes heuristic, intuitive sense here when we look at that final product. So you can really think about it as, 2 pi r, a circumference, for rotating some length around some circle. That's a nice way to kind of remind yourself of how that definition works. All right, any questions? Any questions about our definition? Kind of formula based here. We got a formula. Now let's see if we can use it. Find the surface of a sphere of radius r. So I've drawn a picture of part of a circle. And you can think about taking the top half of the circle and rotating it to generate this sphere. So go ahead and see if you can get these calculations. Now, it's kind of a side note here before we get too far in the calculations. This is one we kind of know, right? We have a formula for this. Remember what the surface area of a sphere is? Sort of. 4/3 pi r cubed is an important value. There wouldn't be an area value. That would be a volume value. We have r cubed. What's interesting, actually, is if I were to take the derivative of that, I would get 4 pi r squared, and that actually is the surface area formula. So 4 pi r squared is kind of the answer here. We know what we're going for. Now let's see if we can get that using our integral. Set up and evaluate integral for the surface area of sphere of radius r. Two things we'll practice using our formula, also putting in the general parameter value. This stuff to ask. Have to work with the neighbor. Here's why it doesn't work off the finish. All right, let's see if we can get this. All right, so we got our formula to start with. We have our formula that looks like 2 pi at radius value times the arc length. So I'm taking that arc length, I'm rotating it about. So for us, that's going to be 2 pi times my function value. So now I have to solve my equation for y to actually get that function. Looks like that will be y equals the square root of r squared minus x squared. So that should be my function piece. Square root of r squared minus x squared. And that arc length piece was 1 plus the derivative squared dx. So now I got to calculate that derivative. So if this is y, then y prime is going to be, well, this is all that stuff raised to the 1/2 power. So take the derivative, I would bring the 1/2 down, take all that stuff and raise it to the negative 1/2 power. But that's just 1 over the square root of r squared minus x squared, times the derivative of the inside function. Don't forget your chain rule here. The derivative of that inside function should give me a negative 2x, so I'll just put that in my numerator, negative 2x. And I can see that 2 is going to cancel out that negative, or that 1/2. So the derivative should look like negative x over the square root of r squared minus x squared. So then I have 1 plus that derivative thing squared. So I will have positive x squared. And I will have the square it, so I'll get r squared minus x squared. And I'm integrating that thing from where to where? I'm adding up all these slices from x equals what to x equals what. Yep.
0 to r.
Not quite 0 to r. Right? 0 to r would be x equals 0 out to the radius value. Negative R, absolutely. From negative R to positive R. All right. And normally this is probably where we chug it into Mathematica, and it can handle that symbolic R just fine. But in this case, it actually doesn't look that bad. I have the product of two roots, so I can really take the square root of this thing times this thing. And if I do that multiplication, I'll get R squared minus X squared. So let me pull out my 2 pi in the front here. I'll take this thing times 1 to get R squared minus X squared. But then this thing times this thing is just going to simplify to plus X squared. I'm like, woohoo! I like that simplification. Now my X squared and my negative X squared and positive X squared are going to cancel out. I just have the square root of R squared, so that's just going to be R. R is not a variable. R is a constant, some fixed radius value, whatever that is. So I can pull it outside of my integral. So I really get 2 pi R times the integral from negative R to R of dx. If I actually want to go through the steps, I'll integrate that to get x evaluated from negative R to R. That's 2 pi R, and then when I evaluate this thing, I'll get R minus a negative R. That's R plus R, so I'll get 2R from this piece. When I multiply that 2R times this, I get 4 pi R squared, which is what we wanted. Yeah.
Where did your negative sign go from square root of 1 plus?
This one? I'll take this one, I'm taking the derivative squared.
Oh, okay.
Right, so I'm squaring, I'll get a positive. Good question. Now make sure you ask about all those little details, because it's really 50-50 whether I made a mistake or not. So might as well ask. Other questions? Right, so this was a known result, but of course it's practice going through the process. We're really just taking that formula and applying it. In this specific case, the simplification turns out really nice. In a lot of cases it won't, so you'll just have to do that integral by some other means. All right, let's set one more up here. We'll just set this one up. We won't actually go through the integration process here. All right, that's what I got. Any questions?
I think I pulled this one from one of the homework assignments. So I really chose it so you could go through it. Just a lot of algebra. A lot of playing with fractions to get a nice form that you can actually do something with.
Okay. My general philosophy is to take these, you run with them a little while, and depending on how tedious they look, you just use math or something. It's good to be good with the algebra, but at the same time, you have to manage your own time, how much time you want to spend on some of these. Any questions about this one? So surface area, and really arc length as well, are just applications of a general formula. All right, now I want to switch gears a little bit and get into 6.7. All right, so 6.7 talks about physics applications. And in a general semester, where we're working out of a different textbook, kind of our standard class, we really spend about 4 days on this section. 2 days on density and center of mass, another day and a half or so on force and work and these other kind of aspects of this section. So we're going to do kind of a condensed version and not focus on it quite so much and spend our time elsewhere. But I do want you to at least be introduced to this idea of density and mass. I think it's an important application of the integral. So hopefully you went through and watched that first 6 minutes of the video to kind of really go through the basics. That video, by the way, was just pulled from www.123mathvids.com, the Calculus 2. And there's really a video for each section that we normally cover in a Calc 2 course. So I've made these before. They're not lecture recordings. They're shorter, condensed versions of a lot of these topics. So we're doing things a little bit differently, so these videos may or not directly apply. But if you get stuck on integration technique, well, that technique is that technique no matter which book you learn it from. So feel free to use these as another resource. I won't assign these, but they're always, other than a few cases, but they're there if you're interested in them. So this was the first video that I did want you to watch from 8.4. So the highlights from that video are just kind of describing density as a ratio. We talked about a mass density. And a mass density could be something of grams per meter or grams per square meter. That gives us a measure of mass over some length or some area or some volume. That would be a mass density. You can also have a weight density. Weight is a little bit different than mass, so you can have a weight density. Give you pounds per square foot or something like that. You can also have different kinds of densities like population per square mile. And that's one we might use a lot on a map or something. So there's other kinds of more general densities as talked about in the video as well. But the big idea was when we're integrating a density with respect to whatever that denominator value is, the result will give us the total change in the numerator value. We already saw this when we integrated a rate of change. A rate of change is kind of like a ratio. We integrated the change in position versus time with respect to time, and we got the change in position. If I were to integrate something that was given in terms of grams per meter, and if I were to integrate that with respect to meters, the result would be total grams. So that was kind of the big idea from the video. Now we'd like to take that idea and apply it now to an example problem. And in it, I want to kind of outline the general process for working with these kind of problems. Oh, sorry, did you need more time up there? Sorry about that. I'll go too fast. Just say stop. Once again, these are highlights from the video, though. So. The total YouTube viewage for the arc length video is still peaked out at about 12-ish. So, all right, everybody good here? All right, so now let's look at a problem that actually goes through this stuff. We're given some region which represents not just some mathy region, but this could represent some thin metal plate. You're working on some project. This is a thin piece of steel-ish thing. The problem is it's not all steel. There's other metals and other things inside of this substance you're working with.
What that tells us is that the density isn't constant throughout this thing. It varies. The material that you're using, this plate, is made out of different things at different parts. So it's more dense some areas and less dense other areas. So we're given a function to talk about the density throughout this region. And our density function is 2x plus 1. That's given to us in grams per square meter. And our goal is to find the total mass of this object.
Well, let's see. Density is grams per square meter. So if I want to find the total mass, it should just be density times what? Times area, right? So can I just take that shaded area and times it by 2x plus 1? Can I do that? Turns out I can't do that for a couple reasons. First, it wouldn't make sense for an area. For an answer. Let's say the area of this thing was 3/8 square meters. Well, if I took 3/8 square meters times 2x plus 1, I'm not going to get a number. But this is a physical plate made out of physical stuff. So when I go to find the mass, I should get a mass of 20 grams. Right, some value. I'm not going to get that if I just take the area and times it by this function. Another reason I can't just do that multiplication is because this area is this whole area. And the density is defined by that function, but it changes throughout this area. The density is different here than it is here. So I can't just take some value here and multiply by the whole area. So I can't do this big problem at once. I can't just take density times area because the density is not constant. So what do? I cut a thin slice. Because if I cut a slice thin enough, if that change in x is small enough, then the density in that thin slice should be about constant. Now if I would draw my slice over here at x equals 0.7, well then I know in that thin slice, the density should be something like 2.4, whatever that number is. It's going to be constant inside of my thin slice, which means inside of my thin slice, if I just try to find the mass in that slice, the mass should really be the density times the area of that slice. I can do it now because the density isn't changing in that slice, because it's small enough. And then I've seen this process before. I want to find the total mass, so I'm just going to add up the mass of all the slices. So the total mass should be taking all these slices and just adding them up, right? Adding them up continuously using the integral. I know what my density is. It's 2x plus 1. And all I really need is the area of the slice. That's the same problem we did when we just did area problems. The area of the slice is just the height times the thickness. The thickness is going to be dx, delta x here, but when I add them all up and take the limit, it will turn into dx. And what's my height in this case?
Square root of x.
Flip those.
Well,
Yep, square root of x minus x squared. That should be the height. And I'm just integrating this through my range of x values from x equals 0 to x equals 1. So really, when you break it down to its core pieces, these mass problems are just area problems. But it's that concept, once again, that's important. I can't find the mass all at once. I'm going to look at a thin strip over which the density is constant and just find the mass in that thin area. And then it's just density times the area of that strip. And then I can generate my integral. All right, any questions about that setup? Okay, well, what if we take that thin metal plate, and it's no longer a thin metal plate, but rather we create a volume by taking that region and rotating it about some axis. And now we have a volume, also made up of non-homogeneous stuff, random stuff in random spots, so that I'm given some other density. Now the density is equal to grams per cubic meter. All right, now I have to have a different density for each volume piece. How would I do this problem? Well, it would essentially be the same thing. I'd have my volume. I would still have to look at an individual slice because the volume would be changing throughout, or the density would be changing throughout the volume. But if I look at a thin slice where the density is constant, then I could say the mass in that slice of volume should just be equal to the density times what? The volume of the slice. Well, what's the volume of the slice going to be? I've done that problem before. It's just going to be pi, in this case, because I'm getting a washer, that would just turn out to be pi times the r big squared minus the r little squared times some thickness, which would be delta x. So it's just that volume problem in disguise. And it really just depends on what the problem is they've given me, how they've defined their density. And that really sums up all these problems. They're going to give me some sort of ratio, grams per meter squared or population per mile. That's my density thing. And I have to integrate that against whatever that denominator piece is. If it's an area, I'm integrating with respect to area. If it's a volume, I'm integrating with volume. All right, one more related question. All right, what if the density was 2y plus 1 grams per meter squared? Find the total mass now. See if you can set up the integral that'll give me the total mass given that new density.
Trying to find the total mass. Can't do it all at once. The density is changing. It's different in different spots. So what do I have to do? What do I have to do? What's the first thing I do? Can't do it all at once, so let's look at a small piece. I'll cut a small slice.
Can I go like this? That doesn't do me any good. Why does that not do me any good? Why can't I cut this slice? Absolutely. If I look at my thin slice, the goal of cutting a thin slice so I can find the mass in this slice. But I can't find the mass inside of the slice because the density is changing. It's more dense up here for bigger y values and less dense down here. Because now my density isn't changing as I go left to right. Now my density is changing if I go up and down. It's now a function of y, not x. The purpose of cutting the slice is to cut it in a region so that if I cut it thin enough, the density will be constant. It's not constant in that slice, but it is constant in this slice. So I should be able to find just the mass of that slice. It should just be the density times the area of that slice. Now what's the area of this slice? Well, it should be the width times the thickness. The thickness is going to be delta y, and I just have to find that width. So I take my equations, solve them for the other variables, and take this one, which is the square root of y, minus this one, oops, which is y squared. To find the total mass then, I just add up all these pieces. Density times the area, integrating from y equals 0 to y equals 1. So why do we stress out so much about finding our area slicing both ways? Because depending on the physical problem, if we're trying to find the mass, it depends on the density. We might have to slice it horizontally if our density is a function of height. All right, any questions about this? Once again, this is just an area problem in skies. Any questions? All right, that's all I want to talk about from section 6.7. Just that first piece. It really just gives us a nice way to not only apply our techniques, our integration process to a physical problem, but it also reinforces the concept of calculus. Big problem, can't do it. Look at a slice, smaller problem, I can do it. All right. So now we're going to get into integration basics. Integration basics. So this is 7.1. Goes through the basic kind of integration processes as a refresher. So we'll start with a little bit of a refresher here. Just the stuff that we reviewed at the beginning of the course. Didn't fit it all in here. We reviewed what the definition of the integral was. We have an integral, we have a limit definition. One version is the limit as n goes to infinity of that Riemann sum. The other version would be the limit as delta t goes to 0. Both are valid here. So we have our limit definition that we reviewed, but that's not how we actually calculated integrals. That would be very tedious. Instead, we use the fundamental theorem to calculate integrals. So we have our how do we calculate it with the fundamental theorem of calculus. And the reason that's so important is because it tells us how we have to proceed to do integrals. We don't have to find out how to take limits of sums, but we have to know how to find antiderivatives. So that's going to be the process of integration. How do we find capital F? How do we find that antiderivative? Once we find that, the rest is easy. And we talked about, so far in chapter 6, all the applications, or representations of integral. Area of the curve, integrating a rate of change to get the total change, the average value, and of course we talked about volumes, areas, volume, surface areas, and now mass. So now our goal is to find more antiderivatives. And the process of finding antiderivatives is really the same process as finding derivatives. There's a limit definition of finding a derivative. It's also ugly. We also don't like to use it. So we use another process. We find the value of some basics. So go ahead and write out this table real quick. And it should be quick. These are ones we should know for the most part. One tricky one off. A lot of these questions in class are to make sure that you know where you stand in this class. It's okay to be behind on topics and just prep more in those topics. I just don't want them to be a surprise for you on a quiz or exam. You can't fill out this table quickly, except for the one tricky one. That's something you absolutely have to review. Any questions about the ones I've written up here? These are the basics that we need to have down. What about the integral of natural log of x? Do we have that one?
Isn't it like 1 plus 1 x?
It's a little weird. It turns out to be x natural log of x minus x, I believe. It's not one we have to memorize. It's kind of an outlier. To actually find this integral, we have to use a technique called integration by parts. And we're going to learn about that in 7.2. So it's not one of the ones you necessarily have to memorize. But there is another one that kind of stands out. So this one doesn't really fit the mold here. We can take the derivative of natural log easy, but we can't integrate it easily. But if we can take the derivative of this to get 1 over x, then I should be able to work with 1 over x. What's the integral of 1 over x? Natural log of absolute value of x. So I want to take a real quick second just to kind of hammer that one home. Right? 1 over x is just x to the negative 1. But you might say, isn't that a power rule application? Yep.
I have a question for the exam.
Yep.
Would you prefer it in fraction format or in power format?
No preference. And no preference at all. It should be whatever helps you best. Right? So a lot of times I'll be integrating fractions and I don't see it. I tend to write these in power form so I can use power rule on them. Right? And then it's kind of however you want to work with it. If you want to simplify something, you should be able to look at it and say, okay, I have it as a power. If I write it as a fraction, is that going to help me simplify anything? And maybe it does. But I have no preference. Other questions? So real quick, if we were taking integrals, right? We had x squared, x to the first, x to the 0, x to the negative 1. We kind of be just attacking these with the power rule. We'd be integrating them. I'd be getting x to the third over 3, x squared over 2, x to the first over 1. Sure, that's valid. I'm essentially integrating a constant. I should get some value of x. But then I get to that x to the negative 1. And if I'm following my rules, it would be x raised to the 0. So far, so good. But divided by 0. And that's the problem. It doesn't fit with our power rule because it'd be undefined. That's why we have to look at this one as kind of a special case. That's why we treat the integral of this thing differently. We know the integral to be natural log of x. So that's kind of maybe something that will just help you remind you of that one. All right. But then there's a bunch of other ones. There's a little table at the beginning of the section that has a whole bunch of other quote-unquote basic derivatives and integrals. And so the question is, are these basics? Do we have to have all these memorized? And I'm kind of torn about these. I really am. There is a reason to have them memorized, and there is a reason why we shouldn't stress on them so much as well. The reason some texts don't put them as basic integrals is because you can generate them using other techniques. They're not kind of fundamental, if you will. So for instance, if I want to find the derivative of tangent, I don't have to have it memorized. I could remind myself that, oh, tangent is just sine over cosine, and I could take the derivative of that fraction using the quotient rule or using the chain rule and the product rule, but I could calculate that derivative just using the basic derivatives of sine and cosine. And so I could remind myself what that value was. Same thing for all the other ones, secant, cosecant, cotangent. I could write them in terms of sine and cosine and then calculate them just from my knowledge of the basics of sine and cosine. So that seems perfectly reasonable. And so if I did that, for example, for this first one, if I went through that process, what would I get as a result? Anyone remember what the derivative of tangent is? Then it'll be secant squared x. And if you went through that process of quotient rule, you get 1 over cosine squared x, which is secant squared x. And so on the one hand, I say, well, do we have to memorize that if we can just go through that process? Maybe not. But the problem is, we might want to integrate secant squared x sometime. And knowing that the derivative of tangent gets us that helps us do the integral very easily as well. Now you could make the argument that there should be another way to integrate secant squared x, and there is, but a lot of those integrals just turn out to be kind of tedious. Right? So knowing some of these core values is very useful. Okay? I'm not going to stress on memorizing all these for an exam. I will tell you that right now. Plus, you'll have your calculators in the exam. So if I expect you to use one of these, you'll have your calculator, so you'll be able to generate kind of that basic values. Any questions about that? I want to explain to you why it is kind of important to still know them, because you'll need to recognize them as well. In some sense, you could say, why do I need to know a lot of my algebra techniques, right? How to write my exponential rules or something. I could just plug those in calculators and get those equal value. That's very true. But if you don't recognize simplifications you can make, you're not able to do certain operations. All right, so we'll point out maybe a couple of these real quick. For instance, if you have arcsine of some number times x, then you take the derivative of that one. You should get 1 over the square root of a squared minus x squared. So it would be the derivative. It should be the derivative of all this. I should kind of clean up my notation a little bit here. And you can go through and kind of work on the other ones as you go. But once again, even these ones, you can generate these values. It's a little trickier to kind of generate these, but we certainly can do it. All right, I think I might come back to the rest of that later. All right, so we have some basic derivatives and integrals that we need to know. And the idea from how we work with derivatives is we extended those ideas. We use some certain properties to generate the value or the derivatives for other functions. So because I can take the derivative of sine of x, I now can also take the derivative of 20 times sine of x because I have certain properties. So I have the derivative of some number times the function is just that number times the derivative of the function. So now instead of just being able to do 5 derivatives, I can do infinitely many derivatives. We have the same thing for integration. The integral of some number times a function is just that number times the integral of the function. The derivative of the sum is the sum of the derivatives. Integral of the sum is the sum of the integrals. And we use those basic properties to do a whole bunch of derivatives and a whole bunch of integrals that we've already been able to do. And then we had a couple more complicated rules. The derivative of a product is the derivative of the first thing times the second plus the first times the derivative of the second. Or whatever way you kind of say that to yourself. There's other ways that people sing that or chant that. So. And we have the derivative of a composition of functions. The derivative of f of g of x is the derivative of the outside function evaluated at the inside times the derivative of the inside function. And so then the question is, do we have integration techniques related to that? How do we integrate the product? How do we integrate a composition of functions? We've actually seen one of these. We've seen that kind of the analogous tool to the chain rule was substitution. We use integration by substitution to, in some sense, reverse the chain rule. We let u equal g of x, and then we plugged that in and did a process to actually do the integration. Now what about the product rule? We're going to have a technique that essentially reverses the product rule as well, and that's going to be called integration by parts. And we're going to talk more about that tomorrow. So as we're getting to the advanced techniques, we'll see that we have these things. We talked about substitution. So the first part of 7.1 really re-stresses that process. So we've summarized this before. We've already reviewed this one a little bit, where we identify that inside function. We're looking for an inside function whose derivative is a factor. We let that be our u. Okay, derivative of u, we solve it for dx. We plug it all in. We write our integral in terms of u, and then we're able to do the integration because it's an easier integral. And then we rewrite our solution in terms of our original variable, x. we've seen that summary before. I think I'm going to skip the one practice. We've done quite a few of those. So I want to talk about some of the other kinds of integrals that your book does here. The rest of section 7.1 isn't so much introducing new techniques, kind of seems like it, but giving you specific examples to kind of give you a tool bag to look at some of these. They give you 5 specific groupings: subtle substitution, split up by fractions, division with rational functions, completing the square and multiplying by 1. And what I want to stress is that pretty much all of these aren't new calculus techniques, they're just algebra. We're using algebra tricks to simplify integrals. Now we're going to use some other integration techniques as we go along. And they're going to be much more complicated than a lot of these. But these tend to be harder to master because they seem to rely on more of an intuition, more of a feel for how we're going to do this. How do you attack a problem when you just see it? Which technique to use, is a little tricky. So there is no better way to get better at these than to practice, practice, practice. Your book has these divided up into separate groups and have a couple problems in each group, so you can kind of see where you struggle the most and keep trying those kind of problems. What I want to focus on is probably these last 3 and talk about some of them in more detail. So, for instance, division with rational functions. Basically what we're going to do is we're going to take this integrand. We have the ratio of 2 polynomials. We have t cubed minus 2 over t plus 1. I don't know how to do that integral. I can't use substitution on it. The derivative of the numerator does not look like the denominator. The denominator does not look like the numerator. I don't have a substitution here. I can't really simplify it like it was this. If it was just over t, that'd be much easier to simplify. I could just write it as 2 different fractions. But I can't actually simplify this using polynomial long division. Woohoo! Some of you guys have really missed this. Haven't used it in a while. You're like, oh, I've been waiting for a chance to use my polynomial long division all these years. Today's the day. A lot of you have probably done synthetic division in high school, which is kind of a new way to teach this. Not a fan, right? I think it hides a lot of the meaning. So I'm just going to demonstrate kind of the old school version and kind of demonstrate how it's very similar to regular division. So as an example, if I said what is 631 divided by 4, you might write this out and do your gazindas. Have you ever heard of gazindas? Say 4 gazinda 4 or 6 how many times? 4 gazinda whatever how many times. That's how you do the long division. Say how many times does 4 go into 6? Well, it goes in 1 time. 1 times 4 is 4. I subtract the 2 values, I get 2. Carry down my 3. How many times does 4 go into 23? And 5. Do the subtraction again, I get 3. Carry down my 1. You guys are all riveted now. Like, yes, division. How many times does 4 go into 31? 7. Get a 28. I get a value of 3. I could add a bunch of decimals if I want. But another way to write our remainder here is I could say my value is 157 plus I have 3 out of 4 left over. And so that's another way to express our remainder. So far, so good? Well, it's exactly the same thing when we do polynomial long division. It really is. I'm going to take t plus 1. I'm going to put it into t cubed minus 2, giving myself a little space here because I got some missing values. And I'm really going to say what number times t will get me to t cubed. Right, like what number times 4 will get me close to 6? Same thing over here. The value would be t squared. T squared times t gets me t cubed. So I do that multiplication. I get t cubed plus t squared. And then I subtract those values, making sure I'm distributing that negative sign though. I'm subtracting that quantity. I get t cubed minus t cubed, that's 0. And I'm left with minus t squared. Okay? I could bring down my negative 2 now, or I could wait. Now I say, what times t gets me negative t squared? negative t. Negative t times that stuff gets me negative t squared minus t. I subtract, careful to distribute my negative sign, negative t squared minus a negative t squared equals 0. I get positive t minus 2. What times t gets me something like t? That would be 1. T plus 1, I subtract that stuff, and I'm left with negative 3. That's my remainder. And so I write all this stuff plus negative 3 over t plus 1. Unfortunately, I'm using t's and plus signs, so it makes it a little more confusing, but that's it. So now I've done the polynomial long divisions. It's just like regular division, except with polynomials. And the whole value here is I've simplified my integrand. Instead of integrating this thing, which I have no idea how to integrate, I can now integrate what it's equal to, which is t squared minus t plus 1 plus, let's just say, I'll just say minus 3 over t plus 1. And I like that. Much easier to integrate. When I integrate this thing, I just get the integral of each of the terms. I get t cubed over 3 minus t squared over 2 plus t minus 3 times the integral of 1 over t plus 1. That's the natural log of t plus 1 plus some constant. If not comfortable with that last integral, it's kind of a, before we do it by substitution, we can let u equal t plus 1. See how that simplifies. All right, so questions about the polynomial long division. So a couple ways you can check your work also. If I do that division, I should be able to take t plus 1 times this thing and get back to t cubed minus 2. So I can always check with multiplication. I can also check with Mathematica. They have a command called polynomial quotient, where you do polynomial quotient and say numerator, comma denominator, comma variable, and it will spit out this part. It'll drop the remainder though. There's also another command called polynomial remainder, which will spit out the remainder. Any questions about this piece? Once again, the goal here is just to do some algebra to make that integrand easier to integrate. And when you have the quotient, that's one tool you could use. There are a couple simpler ways, little shortcuts. Now later when we do a technique called partial fractions, we're going to want to do that long division anytime when the numerator, the degree of that polynomial, is bigger than or equal to the denominator. So this is the case where we would also have to go through polynomial long division. But when they're equal, sometimes there's a trick. So for instance, for this one, I wouldn't use polynomial long division. I would use a little adding 0 trick. I would say, this numerator, I can make it look exactly like the denominator if I want. I just have to add 0. At x squared minus 3. I really want to have minus 3. I'd really like to have that. But of course I can't change the value of the numerator. It was x squared plus 1. But if I write 1 as negative 3 plus 4, makes sense, right? I haven't changed the value of the numerator at all. But now I can really write this as two fractions. I can write this as x squared minus 3 over x squared minus 3 plus 4 over x squared minus 3. And then I can see it simplifies nicely to 1 plus 4 over x squared minus 3. That's what I would get if I did the polynomial long division. So in the case where the powers, the degrees of the polynomials are the same in the numerator and denominator, that's a little trick I can use. Any questions about that one? How many people have never seen polynomial division done like that? Anybody? A couple people? Are they still, for the most part, teaching it that way in high school along with synthetic division? Or not so much? Nobody knows? That was a long time ago, right? Okay. The next topic I want to talk about is completing the square. These are all talked about in the text. I think these are probably the two trickier pieces I like to do a little bit of examples with. So these are two problems right out of the section on completing the square. Of course, they have an example problem, and they have 4 problems related to it. These are two of them that are not assigned. I assigned one from the section. And so the idea is we want to simplify this thing. I don't know how to do it necessarily, by taking these quadratic polynomials that we see and completing the square on those quadratic, and that's somehow going to help us do the integral. And so the tricky part about doing integration is that you have some hints of maybe what technique to use, but they're not rules that are set in stone. You can't say every time you see a quadratic, you want to complete the square on it. So it's good to kind of, once again, build your intuition. Maybe you have a process of what techniques you're going to use. So for instance, these are the exact problems they pulled out of this section. And I looked at that first one and said, boy, I don't want to use completing the square on this one. I can actually just use substitution on that first one. It's a little hard to see the substitution. But if I let u equal that denominator, x squared plus 4x plus 8, and then I take the derivative, I get 2x plus 4, which is really 2 times x plus 2. So it's just a factor times that numerator. So the derivative of the denominator is a factor. Now, how did I see that? I don't know. I just check. I always check for substitution first. I took the derivative. I said, oh yeah, that looks pretty much like x plus 2. Well, except a factor of 2. So there's no kind of magic cure that says this is exactly how you approach every integral. But when you do enough of them, you just kind of look for those things. So if I were to finish this one out, I would solve it for dx. I'll get 1 over 2 times x plus 2 du equals dx. And plug this thing in to get x plus 2 over u. 1 over 2 times x plus 2 du. I get that cancellation that I want. And this integral would be 1/2 the natural log of the absolute value of u. But u is just x squared plus 4x plus 8. And that's going to be a lot easier than completing the square. Should always get us to the same spot, but that's a lot faster of a technique. So I guess the lesson here is don't get attached to one technique. You really want to start looking at all these integrals as broadly as you can. All right? Look for those simplifying tools that will help you. Okay. Now this next one, however, is a much nastier integral to do. So I don't really know how to approach it. I'm kind of thinking about different strategies, and so I might think about will completing the square work. And so I kind of want to have a sense of what's going to happen as I complete the square before I actually go through that process. Well, completing the square just means I'm going to take this quadratic and I want to write it as, I'm going to have some number that kind of gets sucked out of here. I'm going to be able to write the rest, plus or minus, as something squared, as, you know, some number minus theta quantity squared. Well, that's what happens when I complete the square. And I want to write this as just something squared. And in that process, I'm going to remove this number. So I'll have like the sum or difference of squares here. It's okay, well, if I'm going to spend all the time to do that process, is that going to do me any good here? And it kind of will. If I know I can get it to this form, right, this form is basically the square root of a squared minus something squared. And I know how to do the integral of 1 over the square root of number squared minus some variable squared. That's the arc sign. So I feel like if I can complete the square and get to this, then maybe a little substitution will give me that arc sign antiderivative that I want. All right, so that's kind of the thought process that gives me the hint that completing the square is the technique here. Now I got to go through the details. Now I actually got to complete the square here. So I'm just going to work with this piece and complete the square on it. Kind of remind ourselves how to do that. I always forget. I honestly do. It's like dividing by 2 and I'm doing something to it. So if you forget, you just take something and you square it. If I were to take that random one and square it, I would get x squared plus what? How'd you get 6x? 2 times 3 times x, right? 2 times 3 times x. Double the product of those two things, plus, well, I take that 3 and I square it. And so they're basically giving me a couple parts here. I'm going to tweak this a little bit. I'm going to write this as negative theta squared plus 6 theta minus 27. Just a little kinder form here. So they're giving me the first two pieces of that, and the process of complete the square says, I got the first two pieces, I really wish this was different. I really wish this number was the perfect number so that I could write it as some sum squared. So I got to figure out what that magic number is. And so, how do I relate this coefficient to this thing and also to this thing? Well, this coefficient was 2 times 3. I was just doubling this value. So to get back to this value, all I do is cut that number in half. All right, so I just, whatever this number is, that's some b value, that coefficient of the x term. To get back to this one, I just divide it by 2. I take b divided by 2. That will give me this number. And how do I get this last piece, my magic number that I want? Well, I just square that. So I take that b over 2 and I square it. Okay, so let's see. Let me just get this out of the way a little bit. So what that tells me is if I had theta squared plus 6 theta plus 6 divided by 2 quantity squared, well, 6 divided by 2 is 3, squared is 9. If I had this, well, that would be great, because this thing would just be theta plus 3 quantity squared. Okay? So that's what I want. I want this to be 9, but of course I can't change the value, so I'm going to do that same kind of trick that I used in the last problem. I have negative 27, I want plus 9, so really I could think of that as plus 9 minus 27. I'm adding 0 essentially. Or I could say what number plus 9 gets me negative 27. That number would be negative 36. So when I write it like that, I haven't changed the value of what's in parentheses. And now I can write this as negative theta plus 3 squared minus 36, or 36 minus theta plus 3 squared. I've completed the square now. The whole reason I do this is because I can run over the square root of 36 minus theta plus 3 squared d theta. I'm close to my form now. This still looks a little confusing, so I'll get rid of the confusing piece. I will let u equal theta plus 3. If I do that substitution, well then the derivative with respect to theta is just 1. Therefore du is just the same thing as d theta. So when I plug this in, I just get 1 over the square root of 36 minus u squared du. And that's one of those they expect me to recognize. They expect me to see that that's just the arc sine of u over, if this is supposed to be a squared, this is over a, so this is 6. And lastly, I replace my u by what it's equal to. It was equal to theta plus 3 plus constant. Right, kind of long. So it's really important when you get through a long problem like that, you remember the core pieces. The idea was, well, if I could write this in a form like this, I'm pretty close to arc sine. That was the goal. Now how do I write it like this? I do that process of completing the square. We have this, and we're just saying, what number do I want this to be? And what number do I want this to be? I want it to be this number divided by 2 quantity squared. That tells me what number I want here. All right, 2 minutes passed. All right, for tomorrow, bring questions. I have 10 problems from here. If you get stuck on any of the integrals, you want to see them work by hand, bring them. I'll work on them. Otherwise, read section 7.2 and watch the video. Here's your option. There's a video associated with this section, so you can go into Pearson and watch that video. It's 36 minutes long. Right, or you can watch my video on 123 Math Vids. I think it's 10 minutes long, maybe 12, somewhere in there. Okay, totally your option. But watch one of them. Watch one of them go through that process. We want to spend a lot of time going through the details, explanation, integration by parts. We want to use it and practice it. We are also going to have a quiz tomorrow on everything before that 7.2 stuff. Everything through 7.1. So you can just ask questions about 7.1, work through those problems, and we'll have some kind of cumulative quiz at the end of class.
Pushback.